So in this short video, we're trying to prove the Cauchy-Schwartz inequality using these properties that are given, and we're going to consider the function f of t, which is a plus t times b as vectors dotted with itself, a plus t times b. So we're going to try to use these four facts and properties of this function to prove the Cauchy-Schwartz inequality. So it's nice to know that, for example, we can take this property number 4 and use property 3 on it. So for example, here we can write this as tb dot a, and then using property 4 itself, it says the t can actually go back in on the first factor, so this is tb dotted with a, and now if we apply property 2 again, I can reverse the order of these vectors, and it says a dot tb. And so you can now read property number 4 as if there's a scalar multiplying on either side of an inequality, it can either be moved across to the other factor or factored out completely. Similarly, the last property you can reverse. So if I simply take and use property number 3 on both of these, I can see that b plus c dotted with a is the same as b dotted with a plus c dotted with a, where again I've used property number 2 twice, the symmetry of the dot product. And now you can read number 5 as saying either you can distribute the dot product over a sum of vectors on the right or on the left. Obviously these properties are very powerful, otherwise they wouldn't be the only ones we're going to use to prove the Cauchy-Schwartz inequality. So we'll start with the first property. That tells us, since we're dotting the vector a plus tb with itself, it says that that must be a number that's greater than or equal to 0. So we've used the first property to prove that. Now we're going to use the fourth property. We've dotted a plus tb with itself, so I'm going to distribute that as a plus tb dotted with a plus a plus tb dotted with tb. And now I'm going to apply the property that I can do the distributions on the left, which was our first thing we looked at on property number 5. So this is a dot a plus bt dot a, which I'm going to write as t times a dot b, where again I've used this property number 4 and I've reversed the dot product. Here similarly distributing, I've got a dotted with tb, and now in this new and improved version I can write that as t dotted with times the dot product of a and b. And finally I've got tb dotted with tb. Realizing I can move a t across a dot product, so that's t squared times b, and then I can pull it out. I have t squared b dot b. And I know this must be greater than or equal to 0. So I'm going to combine these two middle terms, and I'm going to use the a dot a plus 2t a dot b plus t squared b dot b must be greater than or equal to 0. And now this has to be true for every possible value of t, so I'm going to substitute t equals minus a dot b over b dot b. Okay, and when I do that, when I put that in back into this expression here, I get A dot A minus 2t is A, so minus 2 times A dot B squared over B dot B plus, and now t squared is A dot B squared, and then B dot B all over B dot B squared, because I've squared t. This is greater than or equal to 0. And so if I pull A dot B out of, well, if I simplify this, these are identical terms because this B dot B cancels one of those. And so I have minus 2 of A dot B squared over B dot B plus 1 A dot B squared over B dot B. And so I have A dot A minus A dot B squared over B dot B has to be bigger than or equal to 0. And now simple algebra gives you the result that you want. Move this to the other side and you've got the problem solved. So that was problem number 1. And the second problem involved taking this result and applying it to the vectors A is x, y, z, and B is the vector 1, 1, 1. So A dot A becomes the statement x squared plus y squared plus z squared. B dot B is 1 and 1 squared plus 1 squared plus 1 squared, which is 3. And then A dot B is x plus y plus z. And so the result is a fairly famous inequality, which is, so A dot B squared is x plus y plus z squared. And that has to be less than or equal to 3 times x squared plus y squared plus z squared. Similarly, the next problem asks us to apply the Cauchy-Schwartz inequality when A and B are the same vector. X, y, z. Again, this is going to lead us to an interesting inequality. So the Cauchy-Schwartz inequality again, A dot B squared less than or equal to A dot A times B dot B. In this case, A dot B is x squared plus y squared plus z squared. And so we're going to square that. That's less than or equal to x squared plus y squared plus z squared squared. Ah, of course they're equal. They're not. That's an easy one, right? 3. Problem number 4 was find a vector so that, let's see, A equals -2, 1, 6. And we're supposed to find a B. Let's call it ABC, so that A dot B is 0. In other words, we're trying to find a vector that is perpendicular to the vector 2, -1, 6, trying to figure out what that looks like. So if we simply write out the definition A dot B equals 0, we get -2A plus B plus 6c equals 0. And so we can see that there's an entire plane of vectors that satisfy the equation that that satisfy this dot product equals 0, or that they are perpendicular to vector A. I think this is what we expected, right? I mean, if we're asking what's perpendicular to a vector in 3 space, that's got to be a plane. So there's the equation of that plane. It's a relatively simple thing. If I want to do it in terms of the standard variables, it would be minus 2x plus y plus 6z equals 0. So it's easy to generate points in that plane. This is a very underdetermined equation. You could pick a value for x, a value for y, and then figure out what z is, and that'll give you a one vector. And then if you'd like other vectors in that plane, you simply choose different values. Okay, that's the set of problems, and I hope